All right. Uh, so hey guys, I will be doing an explanations video um, about the problems in starters 46 yesterday. So the contest just ended yesterday, and I finished 66th, and I was able to solve all problems. Um. Okay, so just a quick intro, or like talking about my experience with the with the competition. So I think this one was easier than the previous competitions I had. Um, it's just that I got stuck in one problem. I think it was array sorting. Yeah, I got stuck in array sorting, and then I also had troubles in doing vowel anxiety because I messed up an implementation detail. And that implementation detail was actually to include, like, I forgot that when you're reversing um when you're doing a for loop and you start from the end, you must start with the size of the array minus 1. And what I did was I did this. Like, yeah, I did this in the competition, and I was debugging for 30 minutes, and that's literally just my mistake the whole time. And that's the reason why I keep getting garbage values. And in Visual Studio Code, it actually, like, for some reason, I don't know what C++ this is, but it actually automatically does not print out something that does not exist in Visual Studio Code. But sometimes it prints out garbage values. So what ends up happening is that I don't understand what's going on when I was debugging, but um, when I submitted, it's wrong. But when I test it out here, it doesn't really show the garbage values that much. Like, sometimes it shows up, but sometimes it doesn't, which is weird. But yeah, I kind of wasted 30 minutes, and if I were to solve it 30 minutes earlier, I think I'd place. Where would I place? Probably like around here, like top 30, just top, like something like top 40 or something like that. Pretty similar to my last ranking, but it doesn't really matter that much, does it? Yeah, it doesn't matter. Okay, so now let's explain the problems. Okay, so the first problem is counting words. This is a very easy problem. Again, it's an introduction to programming. And anyone can get this, really, as long as you know how to do programming, or like, or at least you know how to code the most basic stuff. So basically, there are n pages and there's m words. Then how many total words are there? M words per page. So it's literally just n times n, and no further explanation needed to be done there. Okay. Oh, if you're wondering why I'm coughing, and yeah, if you're wondering why I'm coughing, it's basically because I have the virus. Good thing I got vaccinated already, which means that the symptoms weren't severe. Imagine if I didn't get vaccinated, then that means, like, I don't know, I'd probably get a severe case, because I'm very unhealthy and I'm quite, I don't know, like, unfit. So, but luckily I got vaccinated. I think that was last year, or I don't know when I got vaccinated. Maybe like last 5 months or something. But anyways, and that's also the reason why I wasn't able to participate in July cook-off, because I got a high fever, um, on July 3, and I wasn't able to actually, like, I was so weak back then. I think my temperature skyrocketed up to 38.5 or even 38.9, which is crazy, but at least I'm fine now. It's just that the cough that I have, and yeah, there's no cold. I think I'm not um I don't have like a runny nose, so I literally just have cough. Okay. um so math enrollment. So what is this problem? Okay, so basically you have X seats. You currently have X seats, and you have Y students. So what is the minimum number of extra seats you need to get in order to like allow all Y students to sit? So basically, there are three cases. Is that if X is greater than Y, then obviously you don't need to add anyone. If X is equal to Y, or anyone, any chair. If X is equal to Y, just the same. You don't need to add, right? But if X is less than Y, then you have to add Y minus X, um, Y minus X chairs. So the best, like the easiest implementation for that is just to take the maximum of 0 and Y minus X. So this can never be negative because it always um, has this max, it always checks if 0 is the maximum, right? I provided it here because I had a convention to use int long long and then sign made. So this is one of the cons of using this. Basically, like in functions, in like parameters, it only really accepts integers instead of, or 32-bit integers instead of 64. Or like you have to specify still, but yeah, like there's like the difference of data types. Okay. So that's literally just it. So you can check for yourself. Those two are quite easy. Now let's go to um, more difficult problems. So problem letter C. Okay, so group assign. Chef is hosting a party at his house, and then people are invited to it. Then the ith person prefers to be in a group of exact p sub I people. So meaning, um, if you're given an array, so the first person wants to be in a group of people that contains exactly 2 people. The second wants to be in a 3-man group. Okay, the third wants to be in a 2-man group, and so on and so forth. So the first observation that you would see is basically like, okay, um, they must the count of like 2 and the count of 3 must be equal to itself, right? Like this one, you have 3 people that wants to be in a group of 3, so that's nice. But there's also like a case where what if you have this? The idea is that these guys can be grouped and these guys can be grouped, but the number of 2's is actually 4, not 2. But it's still possible. Similarly here, these 3 guys can be grouped, these 3 guys can be grouped. So you can still group them, but this is 3. The number of 3's is 6, is not equal to 3, so the actual condition is to check whether the count, so count of I, the count of I is divisible by I. And that's the condition. So meaning, okay, so um, for all I, um, actually count of do pi. is divisible by pi. Right? So the example here is that this is the count of 2 is 4, is divisible by 2. And the count of 3, which is 6, divisible by 3. So that's the condition, and you can code that for yourself. So how to implement that? Basically, you store the frequencies of each number in the map, and then check whether the value is divisible by the key. And if it is not, then you will print out no. Otherwise, print out yes. Okay, so those are 3 problems are done. Let's go for the fourth easiest problem. This is sort the string. So you have a binary string as of length n. In one operation, you can select a substring of s and reverse it. For example, in reversing substring s24, for s equals 11000, we change 11000 to 10010. Find the minimum number of operations required to sort the binary string, and it can be proven that blah blah blah. So there will always be yeah. So what is the idea in this problem? The idea is that if you have some binary string, the only time where it's not sorted is if there is like a 1 and it is followed by zeros, right? Because it's a binary string. That's the only time where it's not sorted. When it's not sorted, if you have like some form of 10000. Now, if you have multiple of them, right? Then you can you cannot just um sort sort the whole string by turning a substring that includes more than one such case, right? You cannot just sort this because there's always like there are always zeros in between them. So if you reverse it, it doesn't matter. It's still not sorted. So the idea here is that you must count how many cases of like 1 followed by a 0 in the string, and a constructive algorithm of construction of the algorithm for that is just to turn this, and then afterwards you'll get something like this, right? And then you turn this again, so you get that, and so on. Now, what if you have these things, right? Then you can just turn the whole thing, right? You don't want to turn this. So it turns out that the condition is just check the number of, actually not the condition. So basically the count is the number of instances, 10 instances, and that's literally it. So just to look at the example, there's just one such instance, there's 2 such instances, and there's just 2 such instances for this one. So this one is very easy to code. Basically, you just iterate every adjacent pairs, and then check whether whether the first one is 1 and the second one is 0, and you increment if that's the case. If you increment the answer, if that's the case. Okay, let's go to the fifth problem. I don't know if this is the fifth problem, or I guess this is not my fifth problem. Yeah, this isn't my fifth problem. This was my seventh problem that I solved. It was intended to be the seventh problem. Okay, so you're basically you have three distinct prime integers a, b, and c, but you're only given x and y, which are a XOR b and b XOR c, respectively. You also have this z, which is c XOR a, but you're not given that. And then you want to find a, b, and c. And and the given is that at least one integer among x, y, and z is odd. So the first thing is that you're probably puzzled. Why then are you given z? Well, you're given z because um it states that at least one integer amongst x, y, z is odd, right? And this is an important fact later on, right? It will be an important fact in parity. Okay, um, so first observation is that okay. first observation first observation is that you can get z. So you can get z. Um, this is by taking x XOR y. So why is this the case? Because XOR is associative and commutative, just like addition. Meaning x XOR y is just equal to a XOR b XOR b XOR c, and b XOR b is just 0, so we have a XOR c, which is c XOR a, which is c. Okay, now since okay, so this is the first observation. Okay, the next observation is that do we always, like, okay, here's the thing about primes, prime problems. Sometimes a solution is beautiful because you are forced to include 2 in the solution by parity, because 2 is the only even prime. Okay, now this comes from experience, right? You'll always realize this. When I do math, there were so many problems where they give you like some equation that involves primes, and you will just need to prove that 2 is one of the primes, and then everything follows um, by parity. And I have a lot of problems that I remembered that uses that fact, and everything becomes easy after realizing that the problem is one of those. Okay, so how do we attack this? Let's just first review. Actually, yeah. So let's have x and y. So let's examine x and y. So there are actually like four cases, right? Because like 0 XOR 0 equals 0, um, 0 XOR 1 equals 1, 1 XOR 0 equals 1, and 1 XOR 1 equals 0, right? Just a review. So there are four cases. So if x, so what if xi equals 0? So in a bit, right? This is a bit. I call this a bit. These are bits. And yi equals 0. Then what happens is that ai at that point, wait, this is okay, never mind. So ai, so let's do ai, bi, ci can be like 0, 0, 0, or 1, 1, 1, right? So the same thing happens when both of them are 1, right? Because they have the same parity, meaning all of these should be the same as well. Now what if they're different? So this one is 0 and yi is 1. So there are two possible cases. So the first, actually, yeah, there's two possible cases. The first is xi is equal to 0, which, and xi is basically ai xor bi, right? And then this is 0, and the only case when that's the case is if the only cases where this is 0 is if ai is 0 and bi is 0, or ai is 1 and bi is 1. Now yi is 1, and the only case is this one. So combining those two cases, we really only have this case. So 0, 0, 1, or 1, 1, 0, right? Okay. And lastly, um, these are just pretty much the same case. You can just split them. What if the bits are different? What if the bits are the same? But let's just show them explicitly. So if this is 1, then in fact, same argument, they must be different. So ai and bi must be different parity, so it can be 0, 1, or 1, 0. Now yi is a 0, so it must be the same parity with bi, so this must be 1, and this must be 0. Now we have all the cases. We have all the possible cases. Okay. Alright. Now, is it possible? Yeah. Okay. So the given is that the given is that at least one of them are odd, meaning the last bit must contain among the last bits there must be one. See, so these are the possible cases now. Like for the last bit, just replace I with, I don't know, 0 or something. Or is it the first bit or the last bit? Like the bit from the rightmost bit. Okay. All right. Okay. But when we take z, z is x. Z is um, x xor y. Okay. So if z is x xor y, this becomes, all of them become 0. Then here all of them become 0 as well. Or like, uh, wait a minute. Wait, is it odd or even? Oh yeah, odd. Okay. Hmm. Oh wait, this is one, and then this is one. Oh, so this one must be like 0, 1 or 1, 0. Whoops. Okay. My bad. My bad. My bad. But we have to rule out this case, right? Yeah. Let's rule out that case. So basically, um, okay, wait. My PC is getting slower, so I need my fan. Okay. So xi equals 0 and yi equals 0 um, cannot hold for the last bit when I equals 0. Right? So for example, like this. This can never hold when, okay, this can never hold, right? Because the last bit is 0 and the last bit is 0. Why is that? This is, okay, this is because z is equal to x XOR y. Meaning the last bit of z, 0, must also be 0. But at least one of x, y, or z is odd. So this is reject. So we reject this case. Now what do we see in this case? Well, at least one of them are 0. In the other cases, at least one of them are 0. Is 0. Meaning at least one of them is even, and thus one of them is 2. So them means A, B, and C. So now one of them is 2. Okay, right? One of them is 2. And that's why the sample cases, in the sample cases we have this. Alright. Now, this means in all cases, um, in all cases, wait, what is 9 XOR 15? What is 9 XOR 15? 6. Okay. Okay. In all cases, at least one of x, y, and z is even. Not actually at least one, but exactly one. You can check it for yourself, right? You can check it for yourself. Z becomes 0 here, z becomes 1 here, z becomes 1 here. Okay. So, yeah. If x is even, we take the we take A, wait, take A equals 2, wait, actually not, we take 2 XOR, XOR, what did I take, X and 2 XOR Y, or Z, Y and Z. So why is this? Why is this? If we XOR a number with 2, it's taking number with 2. So suppose 2 XOR Y is equal to R. Note that 2 XOR R is equal to Y as well. And R XOR Y equals 2. Meaning 2 XOR Y is equal to B or C, B, like something like that, and 2 XOR Z is equal to C, right? Like if A equals 2 or something like that. But it doesn't really matter because we're ordering it in the end, right? So as long as we get this. Now, why did we not take X XOR 2? We should not take even XOR 2 because the end result will be even. But you only have one even prime 2. And when you XOR 2 with another even, it becomes a different even. Okay, so let's implement that. So my implementation for this problem is to take Z XOR, which is X XOR Y. Now we have to check whether X is even or Y is even. If X is even, then that means Y and Z are odd, so we can just swap X and Z, right? So that we have two odds. If Y is even, then we just swap Y and Z, so that X and Y are both odds. Now we are safe to do XOR with 2, which gives us B and C. It actually doesn't matter if it's if it's B, it's A or C, right? You actually don't know which one. I mean, maybe you can know, but it's too complicated. That's the importance of um, printing A, B, and C in ascending order, which is that you don't actually need to know which one is which, A, B, or C. So you just put it in the answer. Obviously 2 is always the least, so you can literally just print out 2 instead and then just sort these two, but it doesn't matter, just for the beauty of the code. So just place A, B, and C in answer and then sort them and then just print them out. That's what I did. Okay, I think that's 5 problems. Let's do the 6th problem. Okay, what's the 6th problem? Wait a minute, I will just quickly blow my nose. Okay, so you are given an unsorted permutation P of size n, and an operation is defined as swapping two elements that are k apart, basically. Find the maximum value of k such that permutation P can be sorted by applying any finite number of operations. And yeah, a permutation is a permutation of integers from 1 to n appearing exactly once. Okay, so how do we do this? So which one is this? Okay, this one right here. Alright, so how do we do this? So what does it mean when the permutation is sorted? Obviously we know what that means, right? It's like this. Right? It's this. This is the permutation if it's sorted. But what observation can you make? It is that the position of I is equal to I. So Pi is equal to I. So so 1 must be at position 1, 2 must be in the position 2, and so on and so forth. Meaning, if we have an unsorted array or permutation, there exists a number I such that Pi is not equal to I. So an example would be something like this, right? 3 is not in the position 3, it's in the position 2, and 2 is not in the position 2, it's in the position 3. So that doesn't satisfy. Okay, now to permutate it, is it permutate? To permutate it, it must be in the proper position. Okay. For it to go back to the proper position, k must be divisible by their difference. Okay, so for instance, we have 1, 2, 3, 4, 5, 6, right? If k is equal to 2, say this is the position for this one. Then we can then we can have like k equals 2. Then we can swap these, say that, and then we swap this, and then we swap this. So I claim that the maximum is the GCD of all Pi minus I. Where I is from 1 to n that is misplaced. Okay. But would swapping it ruin the other properly placed numbers? Right? It's possible, right? it's possible that this can happen, right? While you're swapping, say this, you swap this, but this becomes misplaced. You swap it another time, this becomes misplaced, right? You get what I mean? So how does that happen? The other numbers can be can does not then have to cover p pi minus I distance if we are adding one misplaced number, right? So while we're moving one number, the other numbers will be ruined, and some other misplaced numbers would have a different distance to cover. It's not pi minus I. But the thing is, the GCD is divisible to all distances. Meaning, if ever we affect other distances, then it's just gonna be different by a multiple of the GCD, which can be covered other time in another time, right? It's still divisible, so you can just fix that later. So that's the point, I think. Yeah. Actually, the idea is that all of them are in different positions. So yeah, never mind. So this is done now. Okay. So it's just literally taking the GCD. So it's just proving if it is in fact sufficient. And how do we do that? Well, what I did was I stored all of the differences, ai minus I minus 1, in an array. Then, in order to take the GCD of a whole array, first you take the first element, and then you take the GCD of the answer with all of the elements. Why is this true? This is because the GCD of, say, A1, A2, AN is just the GCD of A1 and the GCD of A2, AN, meaning the GCD is associative. So you can always just take the GCD of one number and the other groups of numbers, the total GCD of that. So we can always pairwise take the GCD. So an algorithm is just to take the GCD of the first number and the second number, okay, and then that GCD take it with the third number, and that GCD take it with the fourth number, and so on and so forth, and just print out the answer. Okay, and I think that's the sixth problem. Okay, now let's go for a little harder problems. Okay, so this problem is called army training. So you're given N soldiers, and their attack points is AI, their defense points is 1000 minus AI, and they can be assigned attack or defense. So the rating of the army is basically the attack value times the defense value, and the attack value is AI, and the defense value is 1000 minus AI. and those are the sums of all attack type soldiers, and all of the uh, defense value is the sum of defense points of all defense type soldiers, and attack value is the sum of the attack points of all attack type soldiers. And we want to maximize the rating. Okay. So what is the like observation, the main observation in this one? So how do we maximize the product? Definitely by taking numbers that are large as possible, right? We always take the numbers as large as possible. So suppose we have like, right, AI. Suppose we sort A. So we have A0, A1, A2, A3, N minus 1, An minus An. Yeah. Let Bi equals 1000 minus AI. So we have, let's sort B. So we have B0, B1, B2, B3, Bn minus 1. In descending order. Okay. So yeah. So the maximum would be the answer would be the maximum of A 0 plus dot 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 plus AI multiplied by B0 plus dot 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 plus Bn minus I. Yeah, basically this is the answer, because you always want to take the numbers that are as large as possible. And you seek the maximum answer. And this is just a brute force. You don't really have to prove it. Like, you just want to take as large of numbers as possible, and then you take which one will give, which case will give you the largest product. So how do we implement that? Basically, exactly what I did in the solution. We just store an array B in an array Bn. Bi is equal to 1000 minus Ai, and then we sort them both in descending order. And then what you can do is, this is something called prefix sums, and prefix sums is basically just the sum of the first until the last, right? Maybe you can do more math here and probably do a better code. Like, maybe you don't have to create a new array or something like that. You can maybe like multiply it by I times 1000, or n minus I times 1000 minus whatever. But I don't want to complicate stuff. We can just do this, right? And then we can compute all of the prefix sums. Prefix sums is the sum of the first. So basically, pre-I is the sum of the first I numbers in an array. So pre-A, okay. Um, and then the answer is basically just the maximum among all like prefix sums in A times the prefix sums in B. So basically pre-AI times pre-BN minus I. Because um, if you want to take like all of them, right? So if you take I A's, right, then the remaining N minus I must be defense. And notice that you can never really only choose one type because the other will be zero. So if you multiply it, it will be just zero. So it's not good. I may print out the answer. So this is exactly what's gonna output if we try it out. So let's actually try it out just to show you that it works. Okay. So now let's discuss the final problem, which gave me problems in implementation, but I actually got it like, I don't know, 5 minutes. I got the solution in 5 minutes. Okay, so how do we solve this last final problem? So just a summary of the last problem. Basically, we're given a string, and we iterate from left to right, and whenever we encounter a vowel, the previous subarray or substring actually will be reversed. So for instance, we encountered A here, so we're not going to reverse anyone. We're not going to reverse anything. If we encountered E here, we're going to reverse this. And then encountered I here, we're going to reverse all of this. And you can solve it on your own and it will output these things. So how do we do this? So the main observation in this problem that I had was the main observation is that we can always determine or the rightmost um, letters are less likely to be displaced. So this is just a heuristic, right? This is not a rigorous like observation. What I mean about that is like, okay, look at this. J is not gonna get like it's not gonna get bothered. H will only be reversed once. It will only reverse once. So the right letters will be reversed less than less amount of times reversed than those less or equal amount times than those it's left. Okay, so it is a good idea to iterate from right to left. Okay, so yeah, so the realization is that okay, if we iterate from right to left, the first such letters will be appended in the rightmost side, right? It's not going to be reversed. Now after the first vowel, the letters after it will be appended in the front, right? In the front, on the front of the answer string, right? Because you reversed it, meaning it will be in the other side. Now after the second vowel, it will change the parity, meaning these next letters will be appended on the back, like this. Yeah, right here. So that's exactly it. That's exactly the solution. And here, B, C, A, D, A, G, E. Let's do that. After the letter E, it will be appended in the front. So these two letters will be in the front. After letter A, these two letters will be appended in the right, changing the parity, right? And then after this A, B and C will be appended on the front. Now this is just implementation. How do we implement that? The thing about the thing about the thing that is nice about knowing another language is that you can code in another language. This is called front in Tagalog and this is called back. And I'm not sure because there's like methods that's called front, back, push back, and stuff like that. So I don't want to risk doing those things. So I just named it in Tagalog so that it will not interfere with already built-in functions. That's the beauty of knowing another language. So maybe I can even code in Filipino. That would be nicer. So what what's uh, the implementation here? Basically, I defined a map of vowels. If it's a vowel, then it's true. If it isn't, it is not. So we default all other characters to be false. Now, we define a vector of characters called harap and likod, or front and back, and a bool, which is switch. Okay, so what happens here? What happens in the main loop? Basically, we iterate from the back, right? Don't forget to put -1 here if you have a zero indexed array. Then we check first if switch is true, then we put it in the front, right? But initially it is false, so we will always put it first in the back, on the back, at the back. Okay. And then the thing is we should put it after checking this because the vowels itself don't actually get affected by its own. So meaning this E will not go here in the front because it only affects before it. That's why we place it here. Now we check if the character is a vowel. If it is a vowel, then we switch the switch. Meaning, this is another this is a code for this. Basically, we can just negate the switch. This becomes true, and if it's true, this becomes false. If it's false, it becomes true. Okay, so that's the main loop. Now we placed it in the front and the back. And since this is a vector and we're just pushing it back, make sure to reverse likod as well, or back. You want to reverse it. Because basically harap goes like this, so we don't care about it. It's already good. But likod, whenever we append it, we're doing it like this. We want this. That's why we want to reverse it, right? Because if you noticed when I explained my solution, this is like that. If you looked at examples, or if you solve it on your own, whenever we're placing things in the back, we start here and then we keep placing there. If we're placing things in the front, we're placing it like this. Maybe there's a sicker implementation, like kind of like an in place back, or I don't know, and front, in place front, whatever other data type. Maybe like a, I don't know, is it a stack? Is it a queue? Is it a what? Whatever. But I just used a dynamic array called vector. So we just print out the front and then the back. And then let us see if this works. Okay, so it works. And that's pretty much it. That's the solutions for this starters 46. And I gotta admit, this one was a very easy starters 46. I just hoped I was able to participate in July cook-off, which is 2.5 hours, which will be different, right? You need to be, I guess, faster. But either way, I already promoted to the 2 star after my third competition, which is nice. Um, yeah, this is a pretty good graph, I think. And so far, I'm loving it in CodeChef, because I just really think it's very convenient. A lot of things are convenient in this website. Okay, so yep, that's pretty much it, and I hope you guys learned um, something about this problems, and yeah, thanks for watching.